You know, we've all got one of these things in our kitchen, just humming away, keeping our food from going bad. But have you ever really stopped to think about what's going on inside that box? Because it's kind of magic. Today, we're going to pull back the curtain on the incredible science of your refrigerator. Okay, so let's just start with this paradox, right? Your fridge plugs into the wall, it uses electricity, and we all know electricity and the work it does creates heat. So how in the world does it use a power source that makes things hot to make the inside ice cold? It feels like it's breaking a basic law of physics, but, well, it's actually just a super clever trick.
And to get our heads around that trick, we first need to understand what a fridge is really doing. See, the secret isn't about creating cold. Not really. It's all about grabbing the heat that's already inside your fridge and basically kicking it out.
Yeah, officially, this is what it's all about. Moving heat from a cold place to a warmer place. You gotta remember, cold isn't a thing you can just add to something. Cold is just the absence of heat. So your fridge is basically a heat mover. It grabs warmth from your leftovers and physically boots it out into your kitchen. Think about it. In nature, heat only flows one way, right? From hot to cold. A hot cup of coffee always cools down. It never heats itself up. What refrigeration does is it forces that flow to go backward. It makes heat move from the cold space inside the fridge out into the warmer air of your kitchen. And fighting nature like that takes energy. It takes work. And that's what the electricity is for. So how does it actually force heat to go where it doesn't want to go? Well, it all comes down to this really slick, continuous loop, a process called the Vapor-Compression Cycle. This is the hero of our story. And this isn't some niche thing. This four-step process is the absolute workhorse behind pretty much all cooling you can think of. Your fridge, your car's AC, your freezer, even some heating systems. It's just a brilliantly efficient way to move heat from point A to point B. So to really get these 4 steps, let's think about it this way. Imagine the special fluid that's running through the fridge's pipes. The refrigerant is like a heat sponge. The whole process is just a cycle of squeezing the sponge, wringing it out, making it thirsty for heat, and then letting it soak heat up over and over again. It all starts with the compressor. That's the heart of the system, the part that's humming. It takes the refrigerant, which is a gas at this point, and it just squeezes it hard. This is us squeezing our heat sponge. And just like when you squeeze a bike pump, the pressure and the temperature shoot way, way up. Now we've got a really hot, high-pressure gas. Okay, now for the part you can actually go and feel. That super hot gas flows into the big coils on the back or bottom of your fridge. And as it travels through them, it releases all that heat out into your kitchen. That's why it's warm back there. As it sheds its heat, the gas cools down and condenses into a liquid. This is the wringing out step. We've just wrung all the heat out of our sponge. Next up is this moment of really sudden, dramatic change. The high-pressure liquid gets forced through this teeny tiny little nozzle called an expansion valve. And when it does, whoosh, the pressure just plummets. And this sudden drop in pressure makes the refrigerant get intensely cold, turning it into this frosty, low-pressure mist. Our sponge is now cold, dry, and super thirsty to soak up more heat. And finally, this is the magic moment inside the box. That super chilled refrigerant flows through another set of coils, the evaporator coils, inside your fridge and freezer. And here it does exactly what we want. It soaks up all the heat from your milk, your vegetables, everything. As it absorbs that heat, it boils and turns back into a low-pressure gas, ready to head back to the compressor and start the whole cycle over again. Your food gets cold simply because its heat got stolen. Okay, now stick with me, because here comes the big aha moment. If a fridge is just a machine that moves heat from the inside to the outside, what happens if we just flip our perspective? With a refrigerator, your goal is to make the inside cold. You want that cooling effect. The heat it dumps into your kitchen is just a waste product. But with a heat pump, the goal is the exact opposite. You want to make the inside warm. It uses the same process, but it's designed to pump heat from the cold air outside into your warm house. It's literally the same machine, just with a different objective. And the source material puts this perfectly. It says, Refrigerators and heat pumps are essentially the same devices. They differ in their objectives only. The exact same technology that keeps your food from spoiling can actually heat your entire house. Wild, right? And get this relationship is captured in this shockingly simple little equation. If we measure how efficient these machines are using something called the coefficient of performance, or COP, which is basically just the good stuff you get out divided by the energy you put in, you find something amazing. The performance of a heat pump is always exactly one higher than the performance of a refrigerator running in the same conditions. Now here's why that little +1 is a huge deal. It means that a heat pump delivers more heat energy to your house than the electrical energy it uses. How? Because it's not creating heat, it's just moving it. So for every 1 unit of electricity you pay for, it might move 3 or 4 units of free heat from the outside air into your home. That makes it an unbelievably efficient way to stay warm. So we've talked about this cycle, this clever process. But what about the heat sponge itself, the fluid doing all the work? Well, the choice of refrigerant is absolutely critical, and its history is, pretty dramatic. This refrigerant is the lifeblood of the whole system. You need a very special kind of fluid, one that's designed to boil and condense at just the right temperatures and pressures to make this whole cycle work like a charm. And the history of these fluids is a classic story of unintended consequences. We started in the 1800s with effective but really toxic stuff like ammonia. Then, in the 1930s, we invented what seemed like a miracle. CFCs. You probably know them as Freon. They were super effective, non-toxic, totally stable. Perfect. Except in the 1970s, we realized they were literally eating a hole in the ozone layer. So we invented new ozone-safe HFCs to replace them, only to discover later that these are incredibly powerful greenhouse gases. And this table here really shows you the tough spot we're in. We measure the impact with 2 numbers, ozone depletion potential, or ODP, and global warming potential, GWP. Look at the old stuff, R12. Its ODP is set to 1 as the baseline, but its GWP, it's over 10,000 times more powerful than CO2. So we switched to something like R134A. Its ODP is 0. Great, we saved the ozone layer. But its GWP is still 1,300. That's a huge improvement, but it's still a major climate problem. This search for the perfect, do-it-all, harmless refrigerant is one of the biggest engineering challenges we face right now. And that constant search for something better means the story of refrigeration is nowhere near finished. Engineers are constantly coming up with smarter, more efficient ways to move heat around. I mean, people are getting really creative. There are cascade systems that basically stack fridges on top of each other to get down to super low temperatures for scientific research. There are gas refrigeration cycles that are lightweight enough to cool airplanes. And maybe the coolest of all is absorption refrigeration. These are systems that can run on waste heat from a power plant, or even just solar energy, no electricity needed at all.
And that really brings us to the final and most important question. The simple technology humming away in your kitchen is more critical now than it has ever been. As our planet gets warmer, our need for air conditioning and refrigeration is just exploding. So the great challenge we all face is this. How do we use this amazing technology to keep ourselves cool without accidentally making our world even hotter? Something to think about next time you reach for a cold drink. Thanks for tuning in.